Good evening, everyone. Now, as we move on to our second session on our FDP program, entanglement based quantum key distribution, and it's my privilege to welcome you all once again. I now invite Miss Deepika, Assistant Professor, Department of CSE AML, to introduce our resource person of second session, Dr. Kampa Lavanya ma'am.
Thank you, ma'am. Good evening, everyone. It is my privilege to introduce our distinguished speaker for today's session, Dr. Kampa Lavanya, a respected faculty member in the Department of Computer Science and Engineering at Acharya Nagarjuna University, Andhra Pradesh. Dr. Lavanya has made remarkable contributions to research and teaching in the areas of quantum computing, artificial intelligence, machine learning, deep learning, and medical image analysis. She has published several research papers in reputed peer reviewed journals indexed in Scopus, Web of Science, and has presented her work at both national and international conferences. She has been awarded several academic honors and recognitions for her excellence in research and teaching. Dr. Lavanya has been actively engaged in sponsored research projects, including a prestigious DST funded project focusing on the application of advanced computational methods for addressing societal and healthcare challenges. With her extensive expertise and commitment to innovation, Dr. Lavanya continues to guide and mentor students while also contributing to curriculum development and interdisciplinary collaborations. We are truly honored to have Dr. Kampa Lavanya with us today, and I now warmly invite her to take over this session.
So thank you so much for the great introductory. So first of all, I thank organization for giving me this opportunity to share a few idea related to quantum algorithms and cryptography. And with a short period of time, I have taken this opportunity. So I do my best for presenting my topic. So especially, I was very much focus on entanglement based quantum key distribution. So shall I share my screen? If you permit me just a second, then I will allow to give you my presentation.
Yes, ma'am. We will do
Yes,
it.
please respond me. Am I audible?
Yes, ma'am. You are audible. You are
Yes.
audible.
Thank you. Just a minute. I will share my screen.
Yes, ma'am. It's visible.
Yeah. So
Yep.
good evening to all the participants. It's my privilege to take a session on entanglement based quantum key distribution. So let's brief on the discussion of what we are going to see on this 1 hour session. So majorly, I will go with a small introduction because already you have aware from last few days you have been working with quantum technology. So because today it's a emerging area where everybody is talking about the quantum technology, and seriously you people keep hard work on knowing about quantum technology. So not only in the cryptography, there are many other areas where you can work for the quantum computing, because even if you do a 10% of the work, which will be explore more. So so here, actually we already working from the last 2 months for exploring about this quantum technology. We are engaged with a number of faculty development programs, and also we are try to submitting some proposals for the DST. And even everybody is talking about quantum computing, and this is a time where you people need to start working for knowing something about the quantum technology. And I appreciate the organization for taking this initiation to give some idea about quantum cryptography to the participants. So with this, I will move to my discussion. So with this, first we will have a small idea about what is quantum cryptography, and thereby I can move to the entanglement based quantum key distribution, because already the organization committee, they already intimate me, the participants already aware about the quantum key distribution. That's why I just gone for the an advanced quantum key distribution, which is an extension one, and there are number of advantages. We will see all this, and some of the protocols also basically work under this EQKD. So at a short, I can call it as a EQKD. So where we will see some simple numerical example, and we'll also see some demonstration, and some applications in the real world system, because today hardware limitation is there. We can't able to run all the real world examples straight away in the quantum hardware. But anyway, we have a simulators, so we can work some kind of real world systems, real world applications with the uh, quantum simulators. So finally we'll have some challenges and the future directions with this. So let me come to the what is basically a quantum cryptography. So because we already know what is cryptography, a classical cryptography, anyway we know, we have a standard communication channel. So in this standard communication channel, the two parties will be communicated. But the thing is, so while these two parties are communicating, there is a chance of eavesdropping. And this eavesdropping is especially because in the classical computing mechanism, the cutting classical computing mechanism, they are actually depends upon the large numbers. But whereas if you can come to the quantum cryptography, so the quantum cryptography majorly based on the laws of physics, and which will be very much complex to crack. And even now you can observe most of the classical algorithms are already threatened by the quantum cryptography. So this is a time where we definitely move from classical to quantum, because it's an emerging technology, and there it is depending upon the laws of the quantum mechanics. And there is a fast growing to this technology also. So not generally the people are talking about computational criteria. It's not the mean of the computational criteria, because generally the people have a intention that if I can move from classical to cloud computing, or cloud computing to hybrid computing, or hybrid computing to quantum computing, people are simply talking about only the computational capabilities, but it's not matter of the computational capability. So the quantum cryptography, which helps you to strengthen the cryptography mechanism. So once we strengthen the key generation concept, then it automatically provide the more security against the eavesdropping. So this is the basic idea behind to introduce the quantum cryptography rather than the cutting edge standard classical cryptography. So here I would like to give you a basic differentiations among the classical with quantum cryptography. So classical computing rely on the mathematical complexity, that is a large number. They can apply the some extremely large numbers to generate the keys. But whereas your quantum cryptography majorly lays on the laws of the physics. So that will be the major difference what we can observe. That will be the one of the key important point. And the second one is classical cryptography use the large prime numbers, whereas it will use the qubits. I think from the last few days we are talking about the superposition and the qubits. So because these are the um, photons. So these photons they are majorly utilized to implement the cryptography concept here. And already it is proven that the classical cryptography is vulnerable to quantum attacks. Already it is implementing. So they are very threatened to the classical computing. Quantum cryptography, all the quantum algorithms are threatened to the classical computing. And compared to the classical computing, this quantum cryptography is probably more secure, and it will be threatened to the eavesdropping. So this is a simple brief introduction related to the quantum computing. How come it is different from the classical cryptography? Hope I clear with this point. Then next come to the generally the people having a question mark. So why we need to go for the quantum? Already I have given a one of the major reasons why we are coming, because already this is a threat to the quantum computers. So classical algorithm, so called RSA algorithm, ECC algorithm, whatever, they are depending on the hard mathematical calculations. So they are going to be cracked with the exponentially faster, with the seconds. With the seconds, they are seconds, with the minutes, they are going to be cracked by the quantum computers. That is the most important reasons why we are coming for, because already they are going to be cracked within a minutes. Even we can work for the hours and the days for secure communication. That will be threatened by the quantum computer. So this is a reason why we just came for the quantum computers. And the second important one is for future proof security. Because today, so today we are actually working for to strengthen the security, but with a simply with the mathematical or the prime number rely on the complex mathematics, we can't able to sustain to extend the security. So definitely we need the law of physics. So it's a standard one, and it's a proven one. So this quantum cryptography ensures much better security compared to the classical, because it uses the law of physics. So where there are different kinds of the mechanisms they have introduced. So in the law of physics we know superposition concept and entanglement concept, no cleaning theory, so what not, there are different kinds of the concepts which are there in the law of the physics. And you observe, so these are very unbreakable. So if you want to break the security key which is generated by the law of the physics of any one of the mechanism, and which demands for the unlimited computing power, and that computing power today is not at all available. So this is the reason why we definitely demand for the quantum cryptography. And coming to the third and major important one is detection of eavesdropping. So, however, the cryptography evolving better and a better. So eavesdropping also exploring in an equal manner. So it's very big challenge for us to detect the eavesdropping. If you transmit the data, or if you use any kind of standard physical classical networks, and these eavesdropping cannot be tolerated. So that's the reason why instead of classical communication, definitely we need to replace with the quantum communication. So with this quantum communications, then we can able to disturb the eavesdroppers, because the state is continuously changing. And also, if you want to do any kind of intruder deductions instantly, it can be possible. So this is another reasons why we need a quantum cryptography mechanism. And the next important one is, if today the internet is exploring and the technology is exploring, and you can see from small applications to the critical applications, wherever you can go, this artificial intelligence concept or any other related concepts are add on to that. So especially if you can come to the critical applications like a defense or a banking or a healthcare or whatnot, there are different kinds of the sectors which required for the long-term security channels. So these long-term security channels, wherever it is demanding, then you need to have a safeguard for that. So if you apply the safeguard with the classical computing, there is no guarantee of privacy, there is no guarantee of the security, because the data is precious. And the customer is, if you lose the trust of the customer, then automatically there is no sustainability for the products. So today most of the banking applications, healthcare industries, or whatnot, other industries, they are delivering the number of the products, and all these products demanding for the trust. So this trust we can give only by the secure channels. Secure channel we can establish with the quantum computing. So that quantum computing mechanism is especially adapted for the cryptography. So thereby the quantum cryptography is one of the best idea where we can apply the critical applications. And finally, we need to move on to the quantum internet. So because we need to step stone to the quantum networks, we need to step stone for the quantum internet, because if you want to provide any globally secure communication, if you still you are in the classical networks, or you are in the classical internet, there is no future for us. So if you want to become a number one country around the world, so definitely any country or any people, they have to be step on to the a new era, that is so called the quantum networks and as well as the quantum internet. So these are the reasons why we definitely need to go for the quantum cryptography. And now I am majorly focusing on one of the advanced quantum key distribution. That quantum key distribution, because already you have aware of the quantum key distribution, but the problem with the quantum key distribution is, so it will have a qubit which will be generated from the single source, and any qubit which will be generated from the a single source, then there is a question of security. So that is the reason why we need to move beyond that. So if you want to move beyond that, then definitely we need to if extend the generation of the security with the help of the QKD concept. And this QKD is called the entanglement based QKD. So what is basically this entanglement based QKD is used, which use the fundamental property of the quantum entanglement. So what is quantum entanglement? What is the purpose of this? So this particular fundamental property will help to generate the shared cryptography keys between the two distinct parties. For example, we have a party so called A, and we have a party so called the B. There are two parties are there. Then they need to have a secure channel among this for transmitting of the data. So we need to have a secure channel. But if the A is share something to the B and the B want to access with the proper secure, then definitely they need to have a strong key. So in order to generate this particular strong key, there is a core idea which is designed in the entanglement based quantum key. So the first step is you need to have a source. So this source which will produce the entanglement photon pair. So this is called the entangled qubit. So already you know qubit. This is 0R1. 0R1 is the normal qubit. And this is beyond that. This is beyond that. So in this entanglement qubit, so you have to measure, you have to take the measurements performed from both the Alice and the Bob. And these measurements, they are going to be taking Alice and the Bob at the randomly with the help of the strong correlation. So I will tell you with a simple numerical example how to take this entanglement. So these correlation which will allow you to generate the shared random bit string, so which will be treated as a security key. So whenever a eavesdrop is trying to intercept the particles and they wanted to inevitably disturb the correlations whatever it is generated in a earlier step, so this is called the disturbance. So that disturbance is also we need to deductible. So these are the major important core idea that is behind in the entanglement based quantum key distribution. So the first thing is you need to generate the entangled qubit. So how this entangled qubit will be generated? From the sources. So the sources from both the Alice and the Bob. So is it clear up to this? So may I have response from your side?
Yes, ma'am.
Yeah. So now we can look out the what is the standard difference we can observe from the normal QDT quantum. So you can see quantum key distribution and entanglement quantum key distribution. So what are the major changes we can observe? You can see here. So the first important one we can look out for the source. The first thing we should majorly focus on the source. So in case of the QDT, so Alice prepares the quantum state that is called the single photon. There is no a coupled photon here. It is a single one, and generally we know it is a single one, and it will be having some weak pulses. That will be the in a standard QDT. But whereas if you can observe the entangled QDT, so they use the central entangled photon source. So what is central entangled photon source? So I will explain you with the center entangled force. So for example, you see here, this is a station, or we can call it as a device. This is a station, and this particular station will be resided between the Alice and the Bob. For example, if you can take an example of that, right? And this particular station is going to be generate the photon. And this one, this particular compound photon will be utilized by the both the Alice and the Bob to perform the secure communication. And one more important thing is this is purely network friendly. This one is purely network friendly. So that is the major important one, because if you can see, this will consider both qubits. This will consider both the qubit. I just given as a simple notation. It's not just like addition. It's a compound operation. It's a compound operation. One from the Alice and one from the Bob. So like that, it will do some central entanglement photon taking from the both the Alice and the Bob. So that is the source actually it is considering. Coming to the second important difference is the security basis. So in case of the QDT, it is purely device dependent. So there is no cloning theorem, and it is doesn't follow any random basis. It is a standard basis. There is no random basis. So it is, if whenever you can consider the EQKD, it is Bell equality violation. So any device, if it is violate the Bell inequality, then it will have the entanglement, better communication. And the next third important difference, I will tell you what is Bell inequality violation, how to calculate it. I will tell you in a few minutes with my discussion. Coming to the third important difference is device trust. So it requires the trusted sources and trusted detectors, right? Whereas if you can observe the EQKD, even though the devices are untrusted, because if Bell violation is observed, even the Bell violation is observed in the particular devices, still it is going to be handled, the security. That is a third one. And the fourth important difference what we can observe is, so if you can increase the test bits, then there might be chances to increase the error rate in case of the eavesdropping detection. But in case of the EQKD, there might be chances of losing of the entanglement, but a little bit error rate will be uh, much slower compared to the QDT. And coming to the distance and the scalability, so you can have a limited distance and it is limited to the scalability. But if you can observe the EQKD, which will be useful for the long distance quantum internet, then implementation, so definitely it's a complex one. EQKD is a complex one, and there is no exploration on that. Still it is under experiment, but it is progressing. So definitely by the next coming few years, definitely we can have the implementations of the EQKD with a number of the real time applications and the use cases. Anyway, any applications which demands for the future proof and the scalable quantum, and they want to extend the applications for the quantum networks, then definitely we have to go for this one, right? So coming to the protocols, the key protocols that are behind in the mechanism of the QKDT, there are two different kinds of the protocols they are working. One is for E91, and the next one will be BBM92. So we have the two different kinds of the key protocols under this mechanism. The first one is E91, which will be again follow the Bell inequality violation, But whereas if you can observe the Q BBM 92, so the BBM 92 which will be following for the QBR threshold. And device trust anyway, E91 follow the device independent possible, and the next one will be follow the partial trust in the devices. So the complex device E91 E will be much more complex, and it is very simple, and sometimes it is working closer to the BB84. I think BB84 you have already finished in the last sessions. So this is having a theoretical strength, and right now it will be under the D1 QKDT basis, and next this BBM 92 is widely studied and easier to deploy. So now I will move to the before I am going to talk to the E91 protocol. So let me give you a simple example how we can calculate the quantum prediction. So to calculate the quantum prediction, so first of all of you need to know, because the Bell inequality will be the one of the important one. So definitely you need to look on that. So I recommend you to please do some simple exercise for this. Just a second. So we'll have a simple example how to calculate the uh, Bell inequality violation, because it's a key concept. So if you want to do any simulation, definitely you need to know this. So if you have any notes, please make a note down how to calculate Bell inequality violation for entanglement based QDT. So we'll do with step by step, and I will also demonstrate you with Python also, because somebody want to do any research work related to this. This is a start of doing. Someone confirm me, is my screen is visible?
Yes, ma'am. Your screen is
Yeah.
visible. Yes,
Yes,
ma'am.
yes, yes, yes. Uh, so whatever discussion just now I made with you, we'll have a small numerical example. So I ask everybody to please do it along with me. Then it's better to have a idea how the entanglement Q Q QDT is going to be implemented. So we'll go with step one. So first of all, pick up two parties. That is the first important requirement you need to have. So you need to have two important parties. One is so-called the Alice and the second one is the Bob. And already what I mentioned to you, whenever you can work for the UQDT, they have to be considered for the two measurement settings. So you have to take both the Alice measurements and as well as the Bob measurement. So two measurements they are going to be considered, and they are going to be denoted Alice A dash and the B dash. And the outcome will be qubit. So the outcome will be in terms of the binary, and it will be the polarization, and either it to be the +1 or -1. So I think this is the initiation of the entangled QDT. So already initializations we done. So we have already declared the photon pairs, that is called the parties is ready, and the measurements also ready. And now first we will have the correlation. So I already mentioned to you, this will The classical QDT will have the single party which will be generated. But whereas in case of the EQKD, so we have to take the central entangled photon which will be generated from the device. So for that, you need to have the correlation coefficient. So there are different kinds of the correlation coefficients are there. So here I am considering the CHSH or the one of the correlation. So that correlation I was represented with the E of X comma Y. And this sort of the correlation definitely, because we are going to be generating with the help of both Alice and the Bob measurements. That's why we need to consider A dash, B and B dash. So the equation of CHSN is E of A comma B, because there are four possibilities. Because how many measurements are there? Two measurements are there. So definitely how many possibilities we will be getting? 2 square. Four possibilities you will be having. So that is A, B dash, similarly A dash B and A dash B dash. So these are all should be less than or equal to 2. Suppose if it is a classical local realism, that is if you work for the a normal computing, it should be less than or equal to 2. But we are going to be predicting for the quantum. So if it is quantum prediction, it should be greater than 2. So let me check both the versions, classical limit and as well as for the entanglement. Both the things we will see. So in a step 2, if particles are just hidden variables, they are the classical ones. They are going to be using the classical communication with a QDT. But if you got the particles above the greater than 2, then it will be having entanglement communication. So that is, they are going to be resistant, more resistant compared to the classical. So for the quantum mechanisms, if you want to predict the quantum mechanisms on the correlations, whatever correlations already I have mentioned above, if you want to predict the strong correlations, so you need to choose the measurement angles. So what are the measurement angles? For A, I am considering the 0 degrees, and for the A dash 45 degrees. This is just an example I am considering. A dash is a 45 degrees, B equal to 22.5 degrees, and B dash equal to 67.5 degrees. And now you can calculate the quantum correlation. So this is a local correlation and this is a quantum correlation. So how the quantum correlation will be calculated? Based on the CHSH, this is the equation. Cos of 2 theta A minus theta B. So A is related to Alice measurement and B is related to Bob measurement. So let actually start working of the calculations. So parallelly, you also please join and do the calculations. Then only you will have a concept clearly. So first we will see the first possibility, E of A comma B. What is angle with respect to A and B? Can someone respond? What are the angles I defined for A and B?
0 degrees.
Yes, A equal to 0 degrees and B equal to
22.5, ma'am.
yes, 22.5 degrees. Yes. So with this, I am going to be adding those. Cos of 2, one is with respect to Alice and another one is with respect to Bob. So both the measurements I am considering. So if you're considering both the measurements, what is the value I got? I got 0.707. Similarly, you need to calculate for the second possibility. Do it, all of you. So that is A, B dash. This is from the Alice and this is from the Bob. So what are the possibilities? Angles. What are the possibility angles? A and B dash. A will be 0 degrees and B dash will be 67.5 degrees. 67.5 degrees. So now you will be having minus 0.707. This is for the second possibility. This is for the second possibility. Next, let me talk to third one. AB completed, AB dash completed. Now we need to have A dash B. A dash B. So that is A dash will be 45 degrees and the B will be 22.5. So now you got 0.707. And similarly, the fourth possibility also be calculated. So now you can apply all these correlations, apply all the four possible correlations and then compute the S value. How much you got? Tell me. How much value we got? Please respond.
0, ma'am.
0.
0. That means we can't get any, that is less than or equal to 2 means what is its meaning? It's limit to classical. It's a local realism. So definitely we have taken the wrong choice of angles. We have taken the wrong choice of angles. That is, there is no entanglement. So if there is no entanglement, it is equal to your QKD. So definitely we need to have a other possibilities. So we have a wrong choice of angle set. So which does not show any violation. So if it is not showing any violation, Bell's violation, if it is not showing, belt inequality which is not showing, then it is not a entanglement. So definitely what we need to do, we need to alter the angles. Then next take other set of angles. All of you do it. Take another set of the angles. So what are the earlier angles? 0 degrees.
0, 45,
0.
22.5,
Yes, 0, 45, 22.5, 67.5.
67.5.
Yes, if you choose these measurement angles, we not define the entanglement. So that is the reason why definitely you need to alter the angles. So now I am updating my angles for deriving of the inequality. So A equal to 0 degrees, A dash equal to 45 degrees and B equal to 22.5 and B dash equal to minus 22.5. So apply these new set of angles and now you can compute the production. You can see. So this is a new state. This is a new state with alter of angles. You see the possibilities. First possibility 0.707. Second one 0.707. Third one 0.707. Fourth one 0.707. So now apply all the four possibilities. Then calculate state. So what is the value you got? What is the value you got?
2.828.
2.828. So what is its meaning?
It is entangled.
Yes, because S is greater than 2 now. So if it is greater than 2, now this state is having stronger entanglement. So if it is having strong entanglement, it is a more secure channel compared to the classical one. So because it is a quantum entanglement state. So it will give you the QKDT security much better compared to the classical one. Hope this is clear to everybody.
Yes, ma'am. Yes, ma'am.
Yes. So, okay, ma'am, you have given a numerical example. Then later on, if we wanted to establish any such kind of the communication channel, then how can we do it? So, because right now there is no quantum hardware, there is we can't able to create any quantum state, but there is a possibility of doing this with the simulators. So, I will show you that one also.
Excuse me, ma'am. Which platform are you working these, ma'am?
Means
Platform are we working this? Like which?
so I was working with the Python, ma.
Yeah, this platform is Qiskit only, ma'am.
Ah, yes, ma. Yes.
Okay, ma'am. Thank you.
Simulator. Yes, yes. So, do you have any idea about this, ma? Work with Qiskit?
Yes, ma'am. We know in the earlier sessions.
Ah, yes, yes. So, I think you know.
We just heard about the
You
library. That's it.
Yes, yes. Okay. So anyway, I don't want to talk much on this because it's a big thing because as per the application demand, as per the problem statement, definitely we need to go much on exploring about the Qiskit. But as per now, there are normal way of implementing this example. Whatever I explained, we can do it in mathematical and normal Python program also we can able to write, but it's very difficult to write Python code. That's why I'm using this library for implementing of our numerical example. So anyway, first of all of you need to install this, and after that you need to create the bell state. That is what I already mentioned to you. So we need to create the two qubits and two classical bits, because this help you to create the bell state. So this is a one is for the you need to create quantum circuit. That is what, because today there is no hardware is available. So whatever you want to implement, you have to do it a simulation. You need to create the quantum circuits. So here I am creating the quantum circuit with the size of 2 comma 2. So what this 2 comma 2 is indicating, 2 is for the qubits and the another 2 is for the classical bits. So here what are the classical bits, what are the qubits? With this only I'm going to be creating for the bell state. This is the first important thing we need to initiate. And the second important thing is you need to measure the correlation. What is a correlation I am using here? What is a correlation we have used earlier? What is a type of correlation I just mentioned to you? CHSS. This is actually used in the entanglement purpose. That's why definitely we need to have the CH. There is a non-linear correlation coefficient is also there. If you want, you can experiment that also. But as per now, I am using this one only. Okay. So that's the reason why we need to create the bell state. And after creating the bell state, you need to have the measurements according to the angles. So those angles I just given here, right? And there is a some backend also I have used. AR backend I have used. It is also one of the simulator. That one I just consider as a backend here. So just if you want to know something, you can use ChatGPT because it is very helped me lot also to explore more on the quantum technology related to different areas. So this is a backend I have used here, and then we need to define the charts. So there are 4 charts I have defined here. So 4 possibilities. That is what I already mentioned to you. 0001 1011. So like that I have given, because of two bits I have used, 2 parties I have used, Alice and the Bob. And with that there is a dash, B dash I have chosen. So for that, how many possibilities I am getting? 4 possibilities you will be getting. So those 4 possibilities, with that 4 possibilities, we have to calculate the correlation. Then after that, you need to determine the angles. May I know what are the angles we have experimented in the example? What are the two sets of angles we experimented? A 0 degree, A dash 45 degrees, B 22.5. No. First set will be different, right? A
First
0
is
degree,
Mhm.
A 0 degree, 45 degrees, 22.5, 67.5. So those optimal angles I have used here. Those angles I have used here. Check this. Right? And based on this, now I am going to calculating the measures. EAB, that is AB possibilities, and A with BP, and AP with B, and AP BP. So already we have done the same thing in the numerical example. AB. So same 4 measurements I have calculated. Correlation I have done. What is the next step? After correlation, you have to check whether it is violated Bell inequality or not. So in order to do this, you have to apply all these measurements into the formula. So you can check here what is the value we got. 0 we got, right? For the first set of angles. Please respond. For the first set, we got the 0 or not?
Yes, ma'am.
Yes, ma'am.
Yes,
Zero.
same here we got. See that 0.00 something we got. We can consider as a less than 2. Less than 2. That means it's a local communication. It's not having any entanglement. So that is the reason why we need to have the another set. We need to have the another set. There what I consider A 0 degrees, A dash 45 degrees, 22.5 minus 22.5. See this. So these are the new set of angles. I defined with a new set of angles. Now you can see what is S value. So in this way, you can calculate the simple C violation mechanism and determine the state.
Ma'am, I have a doubt here, ma'am.
Yes,
You
please.
have taken it as 4 shots. If you increase the shots, will the value will vary?
Yes, definitely.
So
So
it will be
you will,
it will be greater than 2, or will it go less than 2 in this second case?
it depends upon the angles, whatever you are chosen.
Irrespective of shots.
So if here, if you increase, no, it's depends, ma. It's depends. Somewhere it is depends, because if you wanted to rotate it for the number of the possibilities, then there might be chances to, because it's an experimental study.
Yes.
Experimental study, we have to do it in a uh, both the case. So you have to increase the possibilities, and you have to alter the angles, and wherever you expect for the bell violation, then you need to stop it.
Okay, ma'am.
Yes.
Okay.
So somewhere you can stick on to the number of the possibilities and you can alter it, or you can fix it and you can raise the number of the shots also. But the thing is, if you raise the number of the shots, then computing power will be increased automatically. Yes.
Okay, ma'am. Okay, ma'am. Got it.
Yes.
Thank
Yes.
you, ma'am. Thank you.
Yes. Yes. So this is the way how we can create the entanglement states for the two parties. I hope it is clear for you how to work for the simple examples, and same way how we can simulate it.
Yes, ma'am.
Because this is very key concept, we have to understand properly. With this we can do lot of research also, so we can extend the same idea to the some applications, then there might be a good research also going to be expected. So this is what exactly I covered with you. So we already have a sources. We are already covered with the inequality violation, because inequality violation, if you can extend, then you doesn't have any dependency on the device. You can run it on the device independent. That is a major advantage of moving for the EQKD compared to the standard one. So coming to the first protocol, so we'll start because time is short. Possible, I will cover with the one protocol, and you please extend the same knowledge for the next protocol. If possible, I will extend my discussion. Otherwise, if it depends on the time permit. Then coming to the E91, it is one of the protocol which will be released on the entangled photon pairs that will be shared between the Alice and the Bob. I already mentioned to you, because this is a protocol where exactly follows the Bell's inequality, especially in the form of CHSH correlation. So whatever discussion I just made with you, this is what exactly the E91 protocol which will be utilized. So the key generation purely based on the correlated measurements. Outcome will be purely based on the correlation measurements, right? And this will enable you for the device independent. That is what I already mentioned to you. So it is not purely dependent to only some specific devices. So no need to trust on their missions also. So Alice can will be in the some other device and the Bob will be on the some other device. There is no matter of the how far the device will be trust. Even the devices are not trusted, untrusted also. Sometimes they are going to be have a better communication. So security will be, we are all the time testing with the violation of the bell test. So this is what a simple example. Again, I'm going to be talk to you. All of you, please parallelly work along with me. So we'll see E91 protocol. So I'm already consider the same angles because with the last example we proved that this is a set of the angles which are written to the entanglement. So that's why I have fixed to the same set of the angles: 0 degrees, 45 degrees, and the key basis. And the bob is considering the 22.5 degrees, b dash minus 22.5 degrees, k equal to 0 degrees, k basis. So now the outcome will be qubit plus or minus. This is because this is will be the state. And the bit mapping for both the Alice, if you can map, plus means it's a 0 indicating, minus means it's a 1. And Alice, if it is utilizing the bit mapping, so Bob definitely has to flip on it with respect to key rounds. That is, here we have a single outcome. So if Alice stick on to the plus, then the Bob will be flipped to the minus. That is, if it is 0, it is 1, or if it is 1, it is 0. Like that, they have to flip. And after processing, they have to check for the equality. If it is equal, it's a classical one. If it is unequal, then it will be Bell state. Like that, I'm doing number of the rounds. So in this example, I have considered only nine rounds. So let me check for the first round. So I will start with the Alice 0 degrees, Bob with the basis 0 degrees, and Alice outcome will be plus. If it is Alice outcome will be plus, what is outcome of the Bob? Can someone tell me? Can someone tell me what is outcome of the Bob?
Minus.
Opposite. Opposite.
Minus.
Yes, very good. If it is plus Alice outcome, singlet outcome will be produced by the Bob. That will be the minus. And the key state it will be using. And I just not mentioned the separate column. Separate column. I just given after processing. Yes, please confirm. Bit mapping done. So flipping now we have to apply. Flipping applied at the Bob side only. So after flipping, Check the states of the both Alice and the Bob. Plus is indicating 0 anyway. And Bob outcome after flip will be no one is responding. Yes. Am I audible?
Yes, ma'am.
Yes.
Audible, ma'am.
Are you getting my point or not?
Yes, ma'am.
So the Alice outcome will be plus and the Bob outcome will be minus. That is, take in terms of zeros and ones. Alice outcome will be 0 and the Bob outcome will be 1. After flip, what will be the outcome of the Bob? After flip, what will be the outcome of the blob? This is 0. This will be 1. After flip, this will become 0. This is flip. So Bob flip his bit on key rounds. So this will opposite. So now it will become 0 0. That means it is equality. Equality. Got it? Got it or not?
Yes, ma'am.
So that is for round 1. Similarly, we have to take for the round 2. So in this case, Ali's outcome will be, because it's a random, it's purely on the random nature. 0 0 it is considering key bases, and Alice will be out. Alice will be Alice will be now 1. If Alice will be 1, definitely the Bob will be opposite. That is 0. After flip, it will become 1. Now it will be 1 1. This is called equal. Like that, if you do the rounds 9 times, do the rounds 9 times. Some will be equal, some will be unequal. So you can see. So if it is 0, you can see here, these will be using bell state. And this is also bell state. And this will be bell state. If it is singlet outcome, it will follow the equality relation, equality state. And if it is bell state, it will follow the entanglement. So that is called inequality. So this is the way you have to apply the 9 rounds. Then after that, the next step will be key generation. So you see here, key generation will be based on the equality, and the security test will be based on the Bell inequality check. So you see which rounds are producing the equality? One is producing, right? Next, 2, 4, 6, 8. Right? These are equality used for the key generation. See here. 1, 2, 4, 6, 8. So the secret key will be based on this. You can see here 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, 0. This is after flip, blob after flip. You observe 0, 1, 0, 1, 0, 1, 0. So similarly, non-key rounds. Non-key rounds means security test. If correlation violates CHSH, what is its meaning? There is a entanglement. So if it is entanglement, it's a genuine channel and Eves is absent. Suppose if you got any error rate high, then you need to discard this key and again you have to rotate the rounds for getting a better key generation. And the last step of this algorithm is you need to perform the error correction. So this is about how to implement the E91 algorithm. So the same algorithm you can also apply for simulation. You can use a Qiskit and you can apply this simulation, how to implement this protocol also. Then coming to the next algorithm, BBM 92 protocol. So this is almost moreover equal to BB84 because already you have finished that algorithm. But the only difference what we can observe is it is a entanglement compared to that one. So especially it will use the QBER, that is what already I have mentioned in the earlier. This is help to find out the error rate. So with these two protocols, you can also implement for different real-time applications also, especially for defense applications and for the healthcare applications. These two algorithms we are going to apply in a real time. So you can have a simple example how the number of the rounds which will be coming with the help of the other algorithms. So here also you can have the 6 rounds, and from the 6 rounds you will generated the you have generated the secret key, and with that secret key you can able to have the secure communication. So with this I'm stopping my discussion. So any queries?
Participants, if you have any queries, please ask, ma'am. If not, we'll conclude the session. Okay, ma'am, but we will conclude the session.
Yes, please.
Okay. On behalf of the program coordinators, faculty of our department, and participants, I extend our heartfelt thanks to Dr. Kampa Lavanya ma'am for delivering the informative session. Ma'am, your explanation with paper and the pen, uh, how to solve the Bell inequality and how to calculate the states of CH-SH correlation, how to check the security check, how whether uh, violated or non-violated, and how the systems are whether entangled or entangled. Your explanation and the hands-on approach have greatly enriched our understanding, ma'am. The clarity with your presented this complex concepts supported with the practical insights and results have made this advanced algorithm both accessible and engaging. We truly grateful for the time and knowledge that you have shared with us, ma'am. Thank you once again, ma'am. Thank you so
Thank you
much, ma'am.
so much. Thank you, all the participants, for the great listening. So, my sincere suggestion is start with the simple problems. So, don't think about complex things. First, learn the concept thoroughly because this is a new area where you have to explore a lot. So, this is a beginning. So even myself, I am also trying to uh, getting knowledge on how come this quantum computing is related to another related areas, especially some extent machine learning and already given already some extent machine learning with the quantum is available. So I suggest you to do some real time projects because already all our faculty members. Please encourage your all students doing some simple innovative projects related to the quantum computing because there are in upcoming months there is a huge exploration is happened on this and there are good number of opportunities also coming to the students. Encourage the students to learn the quantum computing, ask them to do some simple projects, and please assist your students also to implement some project. And I sincerely advise all the faculty members, this is a new area and you can work out for the research papers also. If any assistance related to this at any time, you can uh, touch to me. I will be available. My number is there with the organizers. So you please take my contact details and my mail ID also. You please mail to me any assistance related to this or any assistant related to other domains also. I am very much feel to serve. Okay. So thank you so much once again, organizing committee, inviting me, and it's a great honor to meet all of you. So thank you so much. Thank you.
Thank you so much, ma'am. We will do it.
So shall I quit?
Yes, ma'am.
Thank you.
Okay. Thank you so much, ma'am. Yes, the participants, the feedback links are posted in the chat box. Kindly fill them. And so we have an announcement. Please note that unlike our usual sessions at 6 p.m., tomorrow FDP will start at 2 p.m. sharp. We request all the participants you kindly join us at 2 p.m. tomorrow. Tomorrow we have different interesting sessions on at 2 p.m. by Dr. Vishnu on post quantum computing cryptography. Second session at 3:30 p.m. by Surya Prakash sir, how quantum computing breaks the classical encryption. At 5 p.m., we have Fisher investment concepts, uh, quantum secure cryptography systems. At 6:30 p.m., we'll have the valedictory session. And we also, it is followed by online test and also feedback. So thank you so much, participants, for you have joined us and you made uh, the program successful. Thank you so much, all the participants. Please
Thank you.
fill the feedback.
Thank you, madam.